In the figure, ABCD is a parallelogram. In part A, we want to find the orthogonal project of AB and AD. Now to do this, in part A, the orthogonal projection of AB on BD is BP. Using Pythagoras' theorem in the triangle ABP, we have BP squared plus AP squared equals AB squared. So if we subtract AP squared from both sides, we get BP squared equals AB squared minus AP squared. So if we take the square root of both sides, we end up with BP is equal to the square root of AB squared minus AP squared. Now the orthogonal projection of AD on BD is PD. So using Pythagoras' theorem in triangle APD, we have PD squared plus AP squared equals AD squared. If we subtract AP squared from both sides, we get PD squared equals AD squared minus AP squared. And if we take the square root of both sides, we end up with PD equals the square root of AD squared minus AP squared. Now, in part B, we want to prove that AB squared plus AD squared is equal to 2 into AO squared plus BO squared. That is Apollonius' theorem. Now we know that in a parallelogram, the diagonals bisect each other. So that means we're given that O is the midpoint of BD. We want to prove that AB squared plus AD squared is equal to 2 into AO squared plus BO squared. Now we're going to have to do a construction. We draw a perpendicular AP from A to the base BD. This is already drawn in the diagram. So to prove it, we have in triangle BAP, BA squared equals BP squared plus AP squared. That's just Pythagoras' theorem. But BP can be written as BO minus OP. So we have BA squared equals, in brackets, BO minus OP all squared plus AP squared. Now that bracket expands as BO squared minus 2BO times OP plus OP squared. So we have BA squared equals BO squared minus 2BO times OP plus OP squared plus AP squared. We'll call that equation 1. Now in triangle DAP, we have DA squared equals DP squared plus AP squared. Again, that's Pythagoras' theorem. But DP can be written as DO plus OP. So DA squared equals, in brackets, DO plus OP all squared plus AP squared. But DO plus OP squared can be expanded to DO squared plus 2DOOP plus OP squared. And so our equation 2 is DA squared equals DO squared plus 2DO times OP plus OP squared plus AP squared. Now we can add together equations 1 and 2, and we end up with BA squared plus DA squared equals BO squared plus DO squared plus 2 into DO minus BO all times OP plus 2OP squared plus 2AP squared. But we know BO is equal to DO. So that means BO squared plus DO squared can be written as 2BO squared. And 2 DO minus BO all times OP disappears because DO minus BO is nothing. Now if we factorise the last two terms on the right hand side, that simplifies down to BA squared plus DA squared equals 2BO squared plus 2 into OP squared plus AP squared. But if we look at the triangle AOP, From Pythagoras' theorem, we see OP squared plus AP squared equals AO squared. So in the equation, the OP squared plus AP squared becomes AO squared. Now, if we factorise the last two terms in that equation, we get AB squared plus AD squared equals 2 into AO squared plus BO squared, which is the thing that we're required to prove. Now in part C, in the diagram, we're required to prove that AO is equal to OC and BO is equal to OD with the help of vectors. So to solve this, let's first of all call the vector AB small a and the vector AD small b. Then DC is the vector A and BC is the vector B. Now, going from A to C is the same as going from A to B and then B to C. In vector terms, that means vector AC equals vector AB plus vector BC. So the vector AC can be written as small vector A plus small vector B. Now, AO is part way down AC. That means the vector AO is a constant times the vector AC. So let's say AO equals HAC. Now changing AC, we've got AO equals H into vector A plus vector B. Now going from D to B is the same as going from D to A and then A to B. So that means the vector DB equals the vector DA plus the vector AB. But the vector DA is minus the vector AD because they're in opposite directions. And so the vector DB can be written as the vector AB minus the vector AD. So DB can be written as small a minus small b. Now, going from D to O is part way going from D to B. So the vector DO is equal to k times the vector DB, where k is a fraction. So the vector DO is equal to k times the vectors A minus B. Now going from A to O is the same as going from A to D and then D to O. So in vector terms, the vector AO equals the vector AD plus the vector DO. Now DO is k into A minus B. So AO is equal to vector B plus k into vectors A minus B. Now if we equate equation 1 and equation 2, we end up with HA plus HB equals B plus KA minus KB. If we get all the terms with A on one side and all the terms with B on the other side, we get HA minus KA equals B minus KB minus HB. And we can factorise them. H minus KA equals 1 minus K minus H times B. Now that seems to imply that A and B are parallel to each other, because a multiple of one is equal to a multiple of the other. But that's impossible because A is not parallel to B. So the only way this can happen is if the coefficients of A and B are both 0. In other words, H minus K is 0, which implies H is equal to K, and 1 minus K minus H is 0, which implies 1 minus 2H equals 0, or 2H equals 1, so H equals a half, and also because H equals K, K is equal to a half. Now we know AO is equal to H times AC, so AO is equal to a half AC. And also the vector DO is equal to K times the vector DB, so DO is equal to a half DB. Now that means the length AO is equal to half the length AC, and the length DO is a half the length DB, which means that O is the midpoint of both sides. In other words, AO is equal to OC and BO equals OD as required.